Hey everyone! Have you ever looked at a soap bubble and just been amazed by that swirl of colors? Well, it's not just pretty, it's actually a core concept in physics. Today we are going to break down the physics of interference. So whether you're just curious or you're getting ready for a big exam, you are in exactly the right place.
Let's start with something we've all seen, right? A soap bubble. Just look at that mesmerizing shimmer. You see the same kind of rainbow effect on an oil slick after it rains, or even on the wings of a butterfly. But here's the crazy part. None of these things have any colored pigments in them. The colors aren't in the bubble, they're created by the physics of light itself.
So, that's our big question for today. Where do these shimmering, shifting colors actually come from? Well, the answer is a really fascinating phenomenon called interference, and we are about to unpack it together. Okay, so here's our game plan. We'll start with the mystery of the bubble, then get into the core physics of what happens when waves collide. We'll cover the essential rules you absolutely need to know, explain how thin films do their magic, and finally look at some amazing real-world applications. Seriously, think of this as your perfect study guide.
All right, let's dive into Section 1, the rainbow in a bubble. We're about to unlock the secret that connects all those beautiful examples we just mentioned.
So, take a look at these two, an oil slick and a butterfly wing. They seem like they're from totally different worlds, don't they? But in the language of physics, they're basically telling the exact same story. This is thin film interference, and by the time we're done here, you'll see exactly how it all works.
Now, to really get a grip on interference, we have to start with the basics. What happens when waves actually meet? This is the foundational concept, a critical building block for everything else we're going to talk about, so pay close attention here.
And here it is, the superposition principle. You are definitely going to want to remember this name for your exam. It sounds complicated, but it's actually super simple. When waves overlap, you just add them up. A peak plus a peak makes a bigger peak. A peak and a trough, well, they can cancel each other out. So simple, but wow, is it powerful.
I love this slide because it shows you the idea in action. On the left, you've got the textbook drawing, right? Two simple waves adding up to make a bigger one. But look over on the right. That's a real interference pattern, like ripples in a pond. Those alternating bright and dark bands, that's superposition happening right in front of your eyes.
Okay, you ready? This next part is what you've been waiting for. These are the rules. Seriously, think of this section as your exam checklist. These are the key conditions that decide whether or not you'll see a clear interference pattern.
So here's the formal definition. Interference isn't about creating or destroying light. It's about the redistribution of intensity. That's a golden phrase for any exam answer. You're just moving the light energy around, creating bright spots where waves add up and dark spots where they cancel out.
So to get that really clear, stable interference pattern, you need three things to be just right. First, the sources have to be coherent, which basically means their waves are locked in a constant, predictable relationship. Second, having equal amplitudes gives you the best contrast, the brightest brights and the darkest darks. And finally, using monochromatic or single-color light keeps the patterns from getting all smeared together. Remember these three, they are classic exam questions.
All right, now we can finally put it all together and go back to our soap bubble. How does that thin little film of soap and water create all those colors? Let's get into the core mechanism.
This whole thing pretty much boils down to two key events. When a light wave hits the bubble, some of it bounces right off the top surface, but the rest of the light goes through the film, bounces off the bottom surface, and then comes back out. So now you've got two waves coming back to your eye, but one of them has traveled a little bit farther. We call that the path difference. That, combined with a little physics quirk called a phase shift, is what determines everything.
And yep, there's a formula for it. But don't panic. For most exams, you don't need to derive it, you just need to know what the letters mean. It shows that the path difference depends on the film's refractive index mu, its thickness d, and the angle r. And see that d for thickness? That's the real star of the show. It's why the colors on a bubble are always moving and swirling around, because the thickness of that bubble wall is constantly changing.
Okay, screenshot this slide. This is your problem-solving cheat sheet. For a bright spot, we call that constructive interference. The path difference has to be a whole number of wavelengths plus a half. For a dark spot, destructive interference, it's just a whole number of wavelengths. That little half a wavelength is the magic ingredient. And since every color has a different wavelength, lambda, a single thickness will make some colors bright and other colors totally disappear. And poof, you've got a rainbow.
Okay, we've wrestled with the theory. Let's wrap things up by looking at why any of this matters in the real world. This isn't just some abstract concept for a textbook.
It's everywhere.
I mean, the applications are pretty incredible. That anti-glare coating on your glasses or on a camera lens, that's thin film interference at work, designed to create destructive interference for reflected light. Engineers also use it to check if surfaces are perfectly flat with mind-boggling precision. Basically, interference lets us use light as a super precise measuring stick.
This quote just nails it. If a surface isn't perfect, that pattern of light and dark lines, the fringes, gets all wavy and distorted. It literally creates a contour map of tiny microscopic bumps and dips. How cool is that? We're using waves of light to visualize details far too small for our eyes to even notice.
So we'll leave you with this final thought. Now that you understand the physics behind that beautiful shimmer on a soap bubble, start looking around you. What other everyday phenomena, from the tech in your pocket to the nature outside your window, might be secretly shaped by this incredible dance of light waves?